Hello, this is Dr. Liu, and in this video I will review a problem that I did in previous videos. This was in 1D motion, a free fall problem, and in reviewing it I will be doing the energy conservation way. So this way we can compare and contrast the two different methods and which ones we should be taking, and sometimes there aren't any difference, and other times certain things will be better off done obtained in certain ways. So let's first recognize this system as a mechanical energy conservation type of situation. So we have a diver. Diver jumped off the diving board, so the diving board is not even part of the system anymore. So and then she falls into the pool, and she starts at 4 meters per second. That was upward, taking off at a point 1.8 meters above the pool. And then three questions were asked. What is her highest point above the board? And how long time are her feet in the air? Okay, and then what is her velocity when her feet hit the water? So let's try to do this in energy conservation way. So we'll define our system as the diver plus Earth. So we can use gravitational potential energy. Although this portion is more or less implicit, we'll just say we are analyzing the diver's mechanical energy. Although there won't be any potential energy due to gravity if there weren't any Earth, right? So we'll just implicitly pick the Earth as the silent partner. And now we have mechanical energy as a sum of kinetic energy and potential energy due to gravity. I usually try and not use two characters, so I'll use E sub k plus E sub p, gravity. And we have 1/2 mass velocity squared plus mass, gravity, and a vertical coordinate. So this coordinate needs to be decided before we move on to do any numerical calculations. And since the diver is 1.8 meters above the pool, we can set the water surface at 0 height. So let's just say y equals 0 at water surface. So at water surface, and this now we have basically the whole mechanical energy. So let's review. Let's go back, see how much we can get out of the previous question. Here's the discussion here. I even drew a diagram. So let me try to copy this whole thing so that we don't have to redo it. Okay. So far so good. Back to energy. Okay, and I like to have this diagram because potential energy is related to configuration or height. Okay, so I think let me move this a bit just to the left so I can line up with the grid lines. Good. So now we have this. This 2.62 was calculated, right? So it wasn't initially given. Let's just erase that. But everything else was given, and we also have this initial speed. She jumps up at 4.00 meters per second. Okay, so mechanical energy conservation would require us to identify 2 points in time, and we can write this generically as mechanical energy 1 equals mechanical energy 2. 1 and 2, these are 2 points in time. Okay, let's point to these 1 and 2. And we need to identify these points in time. And this question has the whole jumping off, getting the maximum height, and then falling basic, let's see, foot first into the water. So there are two separate future locations, or and later locations if this is chosen to be right here. So let's put this in the circle. Here's 1. 1 means she just jumped off the diving board. So her feet are off the diving board. The diving board is no longer acting on her, and she's entirely under gravity. So remember that that example, the demo with the let's see, what was that, skateboarder, right? Just coming down, up, down, only under gravity's influence that changes her speed. Okay, so now this is 1, and she comes up to the maximum. We can just kind of pause our thought and put a 2 here. So this is second point in time we're interested in. And then she's falling down here, feet first touching the water. Just right before that, we pause our thought, and we put a 3 here. So we'll just have another one, because this question simply has 3 points that are interested to us. So now we have 3 points in time. I like to call these also snapshots, because that's pretty much what they are. You took a camera and you took a snapshot, except that the snapshot, a single snapshot, cannot really record the speed, right? You have to take a couple of snapshots just to see how fast something's moving. So I like to call these snapshots of energy. So in the first snapshot, we'll analyze. So E1, we'll just make it easier. And we'll take a look at what E1 should include: kinetic energy and the potential energy. Okay, so we'll write 1/2 mv1 squared plus mgy1. So everything has 1, indicating they're all obtained at the same exact time. So we know that the diver has a speed of 4.0 meters per second, and also is 1.8 meters above our reference, which is 0 at the water surface. So we'll write this way: 1/2 mass 4 squared plus mass g 1.8. Okay, so that's the mechanical energy. Although we don't really know the diver's mass, we can still factor it out, right? The mass is right here. So 4 is 16 over 2 is 8. So we have an 8. And then we have 9.8 times 1.8. So 9.8 times 1.8. So this is how much total mechanical energy the diver has. Unless we know her mass, we won't really have an exact value, but we'll later realize that every single snapshot of energy will share this factor, so the factor can be divided out. Okay, so now let's bring out our calculator. Okay, so let's calculate this. This is actually, I made a mistake. I just mistyped the plus sign, so here I go again a second time. Sometimes you just have to have a redo. Okay, so 25.64. Let's keep 3 sig figs. So 25.6. Alright, so let's move on to the second energy snapshot when she's at the maximum. So 1/2 mv2 squared plus mgy2. And we know that she has stopped at her maximum height, so this is a 0 v2, and then we can also replace that y2 with y max. And I actually changed this x into y's. That was from a previous iteration trying to record, but I had a wrong number here, so I have to redo the recording, but I didn't really change that back to x. There's no point. So now we have just m times 9.8 times the y max. And according to my equations, E1 and E2 are equal, so I'll state the fact E1 and E2 are equal. And then what is E1 is 25.6m, and E2 is this 9.8 y max m. And let's change color just like I did it before, except I recorded the wrong number. So now we can divide out the mass. And we get Vmax equals 25.6 divided by 9.8. So this is close to be 2.5. But let's bring out our calculator. And as you can see, the last time I recorded the wrong number because I had a wrong sign here. Python is really good. I can keep track of what mistakes I made. Right. So 25.6, I will use the underscore, that is the answer of the previous step, and divide by 9.8. So we have 2.62 meters above the water level. So 2.62 meters. And this is a meter. It's in parentheses. So her point above the board, that means the delta, let's just put it here, this delta y max, let's not use that, let's just say delta y is equal to the difference between these two, 2.6 and 1.8. So 0.82 meters. And let's refer to the last time we had it. So 0.82 meters. That was calculated through the kinematics. Okay, so we're back. Okay, so it seems like we got the same answers. All right, we'll keep moving forward. For time 3 and the energy snapshot 3, let's calculate that. Again, I want to write down this generic format so that I know I have these two parts, energy, kinetic and potential. And this time her feet are at the water level, so she has a 0 height. This y3 is 0. So I have 1/2 m v3 squared plus mg times the 0. So I have 0.5 m v3 squared. Alright, I still have the m, but that's okay. You've seen that I did it. I divided out the m, so the m doesn't really matter, which means if she's a different person or she has a different weight, it would still be the same. If she managed to jump up still at 4.00 meters per second off the same diving board, she would end up being the same. Okay, so now we have E3. Here we have E3 equals E2 equals E1. In E1, I like this E1 because it's simplest. Yeah, there's an M, but this is just one number, right? So I'll do E1 equals E3. That's the same as E2 equals to E3 because they're all equal. I have my preference because this is simple. 25.6 M equals 0.5. Oh, that looks like a 6. 0.5 v3 squared m. Again, we'll divide out the mass, so her mass doesn't matter in this question, and I have v3 squared equals 25.6 over 0.5. Don't ask me how I can get this. I think it's that 51.2. And then we'll need to take a square root, so v3 is equal to 51.2 square root. This I really can't do it myself. I have to use my calculator. So let's do this 25.6 over 0.5 just to check my number. And then take my answer to the 0.5, half power. So 7.16 with 3 sig figs. So here, 7.16 meters per second. Okay. Well, if you haven't noticed, I skipped this question here. How long are her feet in the air? Well, there's no way I can get this answer only with energy conservation. I explained in part of a previous video that energy conservation does not really tell you which way time flows, and it also doesn't contain time. It doesn't concern time, so you cannot solve for time. So here's one major drawback if you're using energy conservation. This is all good, right? This is a very generic argument that you find out energy at these points in time, the snapshots in energy, and then you equate them. It's very interesting. It's very easy to understand. They have to be equal, but they do not get to the time. So I'm going to skip it because we know how to get time. We can just use free fall, right? So to summarize, to solve a problem with energy conservation, we need a diagram so we can see the different types of configuration. Configuration means the height in this case. And if you have a spring, maybe the spring's compression, right? And then we can also kind of mark off the speeds. Here's an auto speed of 0. So let's see, v equals 0, v equals something. We don't know, but we later found out, right? So we mark the points in time that are interesting to us, and then for each point in time, we'll kind of take a snapshot of energy at that time, write it down, and get as detailed as we can. And also picking up some hints such as maximum height means 0 speed, right? And at the bottom here means 0 height, that's 0 potential energy. So once we have this E1, E2, and E3 in the simplest form, which is that, and the E3, I believe that, and we can equate them. And equating them means we're getting equations like this. We're getting equations. So each equation solves an unknown. This as well solves an unknown. This doesn't look like good. Well, okay, here's 7.16 again, right? So here's the very last point. I think I can explain that within the 20 minutes limit I set myself. This is a 3-term equal to each other, one another. How many equations, independent equations, can I derive from this? And you might want to think about it, maybe pause the video. Okay, I hope you paused the video and thought about it. And the amount of independent equations is the same as the amount of equal sign you see. So if you have 1 equals 2 equals 3 energy-wise, you only have 2 independent equations. So the number of unique or independent equations equals the number of equal signs. So you cannot go over the amount. Say if you actually did 1 equals 2, 1 equals 3, then you later did 2 equals 3, you don't really get any new information, right? So this is especially important when we're coming down to, do we have enough mathematical equations to solve unknowns? How many unknowns do we have? How many equations do we have, right? So you need to have your bearings. How many equations you're gonna get with such thing as you have 3 different points in time, you know some information, while they only have 2 equal signs in between, so you only get 2 equations, which is this one and this one. Thank you.